Hey everyone, it's Max, and welcome to the final video in our series about how to make your own encryption app. And this is the app we've been working on so far, and we finished this first tab for the encryption, and then we started working on this some ideas for the second tab for the key exchange in the last two videos. And then we're going to be in this video, we're just going to be finishing up this tab and actually implementing the key exchange. So I've recorded most of the video at this point, and I think it's going to be pretty long. So instead of going through all the development and then showing the demo of the final app, I'm going to show the final app demo first. So we'll get the interesting stuff done first if you just want to see that. And then once that's done, we'll go into all the development footage. First thing I'm going to do is I want to show you guys the rendering issue again in C#. See how this when I take my mouse off, this encrypt gets screwed up, and then like all these other buttons can kind of get messed up as well. So that's because of, I don't know why it does this, but this weird Nahimic service, I'm not sure how to pronounce that. This service causes some weird issues with graphics rendering in WPF apps. So I'm just gonna end this. I'm just gonna stop this service for now before we do the demo. And I think if we do that, the rendering should be better. And let me just check that really quick. Yeah, so now there's no issues with the buttons or the tabs or anything. So the demo should look a lot better. All right, now let's go through a demo showing how this app would work with two people. So first thing we'll do, like always, is we're always gonna have Alice and Bob. And the first thing they're gonna do is use the key exchange tab to come up with a shared secret key. So let's say this top is Alice and this bottom is Bob. So Alice might send a modulus base pair to Bob by first generating the modulus and base using this. So Alice might send Bob something like, your modulus is equal to 39937, and your base is 20,066. So she'll send that to Bob. And again, this notepad right here represents some sort of insecure channel that they're messaging over. So it's assumed that someone can eavesdrop on this channel, in particular, I guess we call her Eve, and can see everything Alice and Bob are writing here. So Bob will receive this modulus base pair, and he can just add that to his key exchange section on his app. Okay, and so now Alice will come up with some private key. Let's say her private key is, 4425. And generate her public key, and Bob will have his private key as well. Let's say that's 3368. So then Bob might say, here's my public key, and his public key is 5887. Alice might say, her public, well, not say, she'll send her public key as well. My public key is this. And so now Alice will receive Bob's public key, and then Bob will receive Alice's public key, and they should both come to the same shared secret key once they have all this information. So Bob comes with the shared secret key of 33862, and Alice should get the same thing, 33862. And now if they go over to their encryption tab, they both are running their Enigma machines on the settings 38, 83, and 22. So now they can start sending messages. So Alice might send some message like, hey, Bob, what movie do you want to see tonight? Oops, tonight. And she'll encrypt that and send that over the insecure channel. Bob will receive it and put that into his encryption tab, and he'll see the message. So he might say, I was thinking about the new Spider-Man. What time should we go? So then Bob will send this. Oh geez, it's pretty long. Maybe I can shrink the font a little bit so it's a little more readable. Do font 12. Okay. Then Alice sees Bob's message, and now Alice can say, how about we meet there at 7 p.m. Alice sends that. Then Bob receives it. And then he just might say something like, okay, sounds good. See you there. So here's an example of Alice and Bob having a conversation, a secret conversation about what movie they want to see and what time they're going to see it. And someone who's eavesdropping on this conversation can't easily crack this code. And so right now, one, they're protected with this ciphertext under the Enigma machine. So that's assuming that they don't have this this app right here. Then they have no way of decoding this as well. But we also talked about for the motivation for this key exchange feature was that we assumed the case of what if some eavesdropper does have this app, then they could just type in these settings into the machine, and then they could just start decoding everything Bob and Alice are writing here. And that's why we wrote the key exchange feature, because now Bob and Alice can, using the Diffie-Hellman key exchange, they can use their private keys and their received public keys. They can just exchange this information, come up with some shared secret set of settings that they never exchange across the insecure channel, but they never really actually knew what they would be until they did all this math, but they ended up computing the same set of, shared secret key in the end. And so now the eavesdropper Eve would have to try and solve the discrete logarithm problem using this information to try and break what this key would be. And I should mention that with actual like secure messaging applications or other applications that use cryptography to secure and send data, most of this kind of like key exchange stuff and the actual encryption and decryption happens like in the background and then before it goes across the insecure channel. So like, when you're using an app like WhatsApp or something, you're not actually receiving ciphertext and having to decipher it. Like, it's just doing all that automatically for you. So it's like doing the encryption and decryption automatically for you. It's also doing key exchange stuff or things similar to a key exchange in the background for you. And I find this stuff interesting, so I thought it would be cool to make an app like this where the people using it kind of see what goes on in the background, but sort of actually see what's sort of going on and have it more these technical details a bit more front facing to the user, just to learn and just sort of see what's going on. I hope this video doesn't turn out too long, but here's a brief summary of the things we're going to do in this video today. The first is we're going to parse the big prime list we downloaded from the previous video. And here, I'll bring that up really quick. That was this list. And this list is the 10th 1 million set of 1 million primes. So I think this goes from this is like 160 million to 179 million. So first we just need a way to parse that list and also decide, how much that list do we want to use, because it might just be a lot of memory just to use all of it. So maybe we'll use like 1,000 or 10,000 elements in it. The second is actually coming up with just building the GUI for this tab. That's all the text fields for like public, private key, the modulus, the base, things like that. And then sort of wire those GUI elements together to actually do the key exchange. And then the final thing that we need to come up with is once we do the key exchange, both parties are going to have some shared secret number, but it's just going to be a single number. So we need to come up with some convention we're going to use to take that single number and then convert it into the three settings here. So like if it's a 6-digit number, we could just take, consecutive sets of 2 digits and put them here. Or, if it's like a 5-digit number, then we can pad it or whatever. We just need to come up with a way that given some number that we can get it, convert it to be these three settings. All right, so let's first parse this big prime list we have here. So the first thing I'm going to do is just delete some of this extra like indents and spaces just to make this easier to parse from the beginning. So this is a much more uniform text file. So we'll just start with this. And since we're not sure what we want to do with this list, I'm just going to make another another project where we're going to figure out how we want to parse this. So this will just be like a prime parser. And we'll give it this list. And yeah, let's just make a new console application. And we've got ourselves 1,000,000 primes. Okay. Okay, so right now we're reading in all the primes from this primes10.txt. So we're making this Streamreader object and we're taking in the file name, and then just while we're not at the end of the stream, read in a line from the file, split that file into an array based on just using the space as the delimiter. And when there are primes, this will become an array of like 6 or 7 elements, and then we'll just start adding those to the array. When there's nothing on the line, this will just have one element in it. It'll just be empty. And then since we're starting at the first element anyway, this for loop doesn't run. So yeah, this goes through and reads all the primes. And since these are 32-bit ints, a 32-bit int is what, 4 bytes, and we have 1,000,000, an array with 1,000,000 elements, so this whole thing is about 4 megabytes. Might be kind of a big file. So maybe we should just make a smaller version of this array with like 10,000 elements and then write that to another file and have that be the file we use for our actual app. Yep, we have a list of 10,000 really big primes that are around 179 million, and we knew 179 million is around where this file ends, so this is looking good. Last thing we need to do is just now write this to a file, to a text file. So let's do that really quick. So, and we'll do that in a similar way. Instead of using a stream reader, we're just going to use a Streamreader to write these to a file. So we'll say using Streamreader SW, assign new Streamreader, and this will be primes.txt for our case. This will be our small list. And we'll just say sw.write. What does write do? Writes to the stream. I guess we'll just write a line. And we will write primes. I guess we should say for int n assigned 0, while n is less than primes small list dot length. So for each element in that smaller prime list we have, we're just going to write one line to this file. So sw.writeLine primes list small sub n dot toString. And yeah, so this should just go through each element in this smaller primes list and then write that as a line to this primes.txt file. And when we do that, it should be a new file in this bin debug directory here. So let's run this and give it a try. Nothing crashed. That's good. We have a primes.txt file in here. Let's look at it. And cool. We have a long list of primes that's all around 179 million. But okay, this is a nicely sized file. So let's take this file and put it in the bin debug directory of our app. So now we'll have access to these primes, and these will be the primes we use for the modulus for the Diffie-Hellman key exchange. Okay, now for item 2, which is to start building the GUI for the key exchange section. So let's open up our solution file and then navigate to the XAML section, and we'll go to the key exchange tab. And now we can start building the GUI from here. So for the first thing, we'll just add some text fields to represent all of the main parts of the key exchange. So like the modulus, base, public, private key, things like that. Okay, so we've got the modulus, the base, our private key, the public key we create from these 3 fields, the received public key from the other party, and then the shared secret key that both of us will come to. And one thing that I'm going to do here actually is I'm actually going to color code these text fields just as a way of indicating which variables are private and which variables are public. Okay, cool. So now we have the moduluses and the base, we have our public information highlighted green and our private information highlighted red. And this is just a good reminder for whoever's using the app. Like if you're going to send someone information from this tab, make sure it's from one of these green boxes. The next thing we're going to want to do is we're going to want to add some buttons to do some of the computation we want. So the first button we're going to want a button that's going to automatically generate a base and modulus pair for the user. So let's add that. All right, so now we've got the 3 buttons that are going to do most of the sort of number crunching for us. We have the first button to generate a base modulus pair, and then a second button for generating a public key given our private key, base, and modulus, and then the last button for taking the received public key we get from the other person and our private key and everything else, and then computing the final shared secret key that we'll both use for coming up with these settings for the Enigma machine. All right, now that we've got all of the user interface elements laid out, let's start actually programming some of this stuff. So first, let's just let's go into our main app and let's get some more variables in to represent the data we're going to be using for the key exchange. So we're going to have a couple things. We're going to have ints, or I guess we're going to have unsigned ints actually for our modulus, our base, which we're just going to call G, our private key, which I guess we'll just call PK. And what else do we have? We have our modulus base private key. We're going to have a public key. Oh, private and public key are both P, so maybe we'll do private. Maybe we'll just say private key, public key. Then there's the received public key, so maybe we'll have our public key. And then last is the shared secret key, so maybe just shared secret key. So we have data for all of these text fields. We're also going to have an int array for our primes. We assign new int array, and there's 10,000 elements in this list. So we have our prime list. And actually, yeah, so one thing we need to do is we need to fill up this prime list the moment we start the app. So in here, we'll have something like load primes. And yeah, let's actually write load primes really quick. So let's try it again. Load primes, ran, didn't crash. And we have all these primes. Okay, and I'm just gonna just want to add this to the watch really quick so I can scroll to the bottom, make sure that it's fully populated, and it is. Cool. Okay, so now when the app starts up, it loads the primes into memory, so that's good. Okay, so the first thing let's do is let's code up this generate modulus and base button. So this is just going to automatically generate a modulus and base for the user, so they don't have to. And one of the things we'll do is we'll randomly pick a prime, and then we'll pick the base to make sure we never have an int overflow during our modular exponentiation. Oh, and actually, now that I mention the modular exponentiation, let's pull over that function we made from the last video into this app as well, because we're going to need to do that to compute the to do all the modular exponents. So let me just grab that really quick. So I'm just copy and pasting from the source file we worked on in the last video. So this should look familiar. Okay. So now we need to randomly pick some element between, actually wait, whoops. Some element randomly between 0 and 10,000 minus 1 to randomly pick a prime. And then like we talked about in our last video, we just need to make sure that this never overflows. And so the largest value y can be is constrained by the prime we pick. So y can never be bigger than whatever our prime is minus 1. So we just need to make sure that the prime we pick minus 1 times our base never exceeds 32 bits, so 2 to the 32 minus 1. So once we pick our prime, we just need to make sure that a is less than 2 to the 32 minus 1 divided by our prime minus 1. So first, let's get a random index. So so we need to now pick g is going to be some random number. And we definitely don't want g to be 0, because we don't want g to be 0 or 1, because then the equation is just really trivial. So we'll start at 2. And then the biggest thing we want g to be is 2 to the 32 minus 1 divided by p minus 1. All right, so now we have our generate modulus and base button all coded up. And so what this is going to do is, first we're randomly going to pick some number between 0 and 10,000 to just randomly pick a prime. And that'll be assigned to our modulus variable here. And then we're going to randomly pick our base as some number between 2 and 2 to the 32 minus 1, so the upper bound of the 32-bit uint, divided by the prime we selected minus 1. And that's just to make sure, again, that this intermediate multiplication never overflows during the modular exponentiation. And the lower bound's at 2, because if we made this a 0 or 1, then trying to solve the discrete logarithm problem would kind of be trivial. So the lowest number we want for a base is 2. And then once we get those two values, we're going to display them in the text box. So let's just test out this button and make sure it works. Okay, base of 3 and some big prime. 9 and some big prime. I feel like our bases are kind of small, but maybe that's just because of how big our prime is, actually. Which is okay. Our bases don't have to be big. Actually, let's just do that math. If we do 100 and... Let's check that really quick, actually. Let's go to Wolfram. Let's go to Wolfram Alpha. And let's look at 2 to the 32 minus 1 divided by our prime. How big can that get? Oh, okay, it can really only get to 23 without overflowing. Okay, that's fine. The base doesn't have to be a super big number anyway. So this looks like it's working properly to make sure we never overflow with this big prime we have. So that looks good. The next thing we need to code up is our generate public key button. So let's start doing that. In order for the generate public key button to work, these two fields have to be filled in with a modulus and base pair, and then the private key also needs to be filled in as well. And one thing I should just mention early on, or I should just mention, is that there's not a lot of exception handling in this app. So like, you need to really make sure that the correct values are filled in at the correct times that each of these buttons is clicked. You know, once you download this app or download the source code and build it yourself, you can start adding your own exception handling to the app. So like making sure that, you know, the numbers people type in are valid numbers, making sure they're not negative, making sure they're not text, making sure you get appropriate warning messages when you click a button when you're not supposed to, things like that. But for right now, we're going to have very minimal exception handling and just make sure the user uses the app properly. Yeah, I haven't focused that much on exception handling, but I tried to focus on the exception handling that's not really trivial. What I mean by trivial exception handling is like, we all know, like, of course, you probably shouldn't put in a word for the base, right? We know it should be a number. So I think that's kind of obvious that if someone's going to try and make this app more robust later, they'll know to do that. But some of the less obvious exception handling is kind of like doing this stuff, right? Like making sure that based on the modulus you pick, to pick your base such that your intermediate multiplication never has an int overflow. So those are kind of more subtle, like application specific type exceptions that I just wanted to make sure we catch or prevent. But the sort of basic exception handling, I'm just not going to worry about. It's just kind of not really the main part of the content for the series. With that said, let's start writing the code for this public key generation. So when we're writing this, we're assuming that we already have a private key in this field. So we could also make a button to generate a private key. I feel like we don't really need to though, and the user can just pick their own private key, and that'll make it, you know, truly private in case they're concerned about the app knowing something. And in order to make this secure, you know, I mean, the bigger the private key, the better. All right, so this should be really all we need for the public key generation. We'll grab the private key from the text box that the user types in, convert it to an int, and then cast it to the unsigned int here, and then compute the public key by doing, you know, the base we selected raised to our private key mod p, which is our modulus just called mod, and then we'll actually fill in the text box with the public key we just generated. So let's give that a try really quick. Just make sure it works. So here's some base pair we just picked, and we'll also get Wolfram Alpha to test this as well. So let's pretend our private key is 333,333. So we'll have 2 to the power of 333,333 mod this modulus, and this should be our public key that we generate. So the public key looks like it's 100,983,462. So let's just make sure that we get that as well. And we got 100,983,462. Cool. So looks like the generating public key button's working well. Okay. So now last thing we need to do is generate the shared secret key. So let's start coding that up. And now similarly to the method we had for generating the public key, when we generate the shared secret key, we're assuming we have data in this receive public key text box. And so this receive public key is something that's going to get manually entered by us because it's going to be given to us by the other party. We're going to assume we received their public key, and then we're going to use that in combination with the modulus base and our private key to come up with the shared secret key. So now let's do that here. So we're going to say the receive public key is just equal to, I'm just going to copy this line actually, but instead of the private key text box, it's the received public key text box. If I can spell right. Receive public key text box, okay. And then the shared secret key. Again, it's going to be a very similar method to the method we just wrote. So shared secret key is equal to, okay, so the base now is going to be their public key, so the thing we just got. And then the exponent is still going to be our private key and computed to and modded the same modulus. And so we'll say shared secret key text box dot text signed public key dot not public key shared secret key dot toString. So I just ran into an issue with the app that I want to show you guys, and it's something we're going to need to fix before we move on. Let's do just bringing up the key exchange tab again, and we're also going to bring up Wolfram Alpha. And one thing I'm noticing is the shared secret key is not being computed correctly. So let's just go over an example really quick. Here's a modulus base pair. Let's say our private key is 3,333. We generate a shared public key, and let's just make sure this is right with Wolfram Alpha. So our base will be 14. Our private key is 3333, and our modulus is this 179 million number. Okay. And we get, what is that? 6.3 million? 6.3 million 164. Okay, so this looks good. Now, let's say we get, so this is our public key. Let's say we get a public key from the other person that's like, let's say it's like 5 million. Let's say 5.3 million 100, something like that. Then we generate a shared secret key. Oh, whoops, it was just a breakpoint, my mistake. Okay, so we have a shared secret key, and now let's do the same thing in Wolfram Alpha. So we should be able to compute the shared secret key. We take the received public key raised to our private key, mod this, and they get, what is this, 40,483,429, and we got 15,020,675. So we're getting completely different numbers. So yeah, and so what's happening is this is a perfect example of where like C# is doing something really wrong and it's not telling us. So we're actually still overflowing in here. And the reason we're overflowing is even though we put a constraint on the original base to make sure that never overflows, when we generate our public key, there's not an appropriate constraint on the other person's public key when we're computing the shared secret key. So yeah, let me show everyone what I mean by that. So let's say y1 is equal to a to the b mod p. And in this case, like a is the base, b would be like our private key, for example, and y1 would be our public key, and then p is the modulus. So we knew from the last video that in order to prevent this from overflowing, we needed to have a be less than 2 to the 32 minus 1 divided by p minus 1. And when we picked p, we ensured that a follows this inequality to make sure we never get an int overflow in our intermediate multiplication for the modular exponentiation here. However, here's the problem. When we're computing the shared secret key, we're basically doing this operation, or doing this, evaluating this equation, we're getting y1, and then we're using this as our new base. So then we're doing something like y2 is assigned y1 to the power of b mod p. And now we haven't done anything to make sure y1 is constrained by this. And if we just take an example, so let's just see, like, how big can a be, right? So if we actually do 2 to the 32 minus 1 divided by our prime, which is like 179 million, like how big can that be? And I think it was around like 20s or 30s. So if we do 23 or 2 to the power of 32 minus 1 divided by like 179 million, 1, 2, 3, 1, 2, 3. I think it's 179 million. That might be off. Yeah, I think this is 179 million, 100,000, yeah. So we get about 23, 24. So if we floor this, 23. So it means that in order to guarantee that this never overflows for p equals to like 179 million. This y1 must be less than 23. And there's no guarantee of that, right? Because like the only guarantee is that y1 is less than, is going to be at most p minus 1. So now we need to figure out some way to not like arbitrarily pick our p. We need to pick some prime such that no matter what we get out of our modular arithmetic, this never becomes less than 2 to the 32 minus 1, I guess. So now what we need to do is figure out some bound for p. I think last time when we were originally coming up with values for primes, we just kind of said like, oh, like let's just get some pretty big prime numbers and just that should be fine. And then, you know, the worst case scenario we'll have in our multiplication is resulted in this inequality. Basically, our base times p minus 1 is the biggest thing we'll ever get, and make sure the biggest thing we'll ever get is less than 2 to the 32 minus 1. But now that we're going through some more of the key exchange, we're realizing, oh, actually, you know, we're replacing our original base with some bigger base, which is the public key, and now that's overflowing. So, but we're still keeping the same modulus. So really, the worst thing that can happen is not a times p minus 1, but p minus 1 squared. So really, we want to make sure that p minus 1, we still want to have this constraint as well, but we also want to make sure that p minus 1 squared is always less than 2 to the 32 minus 1. So if we were to solve for this, what would our prime limit be now? So if we just said like 2 to 32 minus 1, let's just take the square root of that. And that will sort of limit what our biggest prime is. Oh, and yeah, well, of course it's around 16-bit. So this is saying, you know, our primes have to be in the range of some number under 65,000. Yeah, so in order to guarantee this never happens, we need to have primes that are much smaller than this 179 million. Or we either need, if we want to have these giant primes, we either need to increase the data type or use those arbitrarily large like integer type objects I mentioned earlier. I'm going to go sort of off screen, look at those prime lists again, and sort of regenerate a new list of primes that we'll use for the app. So let me go do that, and I'll be right back. I just finished coming up with a new list of primes, and they're right here. And now this is a list of about 3,000 primes that range from 20,000 to 56,000 here. And so now all these primes are less than, I think we're trying to get a prime less than, instead of 2 to the 32, we're looking for 2 to the 16 minus 1. So what I did to get those was I went back to that website we had where we downloaded the first 10 million, or the 10th 1 million set of primes. And instead of picking the 10th set, I just picked the first million primes. And specifically from there, I selected the first, sorry, not the first, primes 2,000 to 5,000. This list right here is basically, you know, with an error of maybe plus minus 1, the 2,000th prime here, and then this is the 5,000th prime here. So I'm going to take that list I just generated now, and again, this is the same app to parse it basically, except some of the spacing was a little different, so I had to go through every time I read a line of primes, and I actually had to go through and remove the spaces before I added it to the primes array. But other than that, this is basically the same parsing script, except with the removal of spaces, and for the creating the small list, only adding the primes from 2,000 to 5,000, or sorry, the 2,000th prime to the 5,000th prime. So let me now take that file I just made and put it into our app. So let's see, here's our app. Gonna replace this file. Now, yep, now it's much smaller. So now we have the smaller text file. Let's try creating our shared secret key again, and hopefully we don't get any of the overflows. So we're going to bring up Wolfram Alpha again. Start up the app. Generate a base modulus pair. And now we get something like this. Now we have a much bigger base actually to prevent the overflow as well. So our private key now is 3333. Okay, so let's try this now. So we have our base raised to our private key mod p. And we get 19,227. Let's see if we get that. Oh, yeah, that is what we got for our public key. Cool. Now let's say we receive some public key of 22,222 and generate our shared secret. And it looks like the shared secret now is 22,998. So let's try that. So that's our received public key raised to our private key mod 35,371 or 35,731. And cool. Now we get the result matching Wolfram Alpha of 22,988. And yeah, that's something I definitely overlooked when we were first talking about this modular exponentiation. You know, I was looking at this and saying, okay, we need to make sure this never overflows. So let's pick a base that never makes this overflow. You know, like I said, as I forgot, this public key can be much bigger than the constraint we put on the base. So we had to actually limit the range of our primes in order to make sure that generating the secret key also never overflows as well. My mistake, and kind of took us on a detour for this video, but now that we have that fixed, we can start getting back into the into finishing the app. We've now finished items 2 and 3, so the last thing we need to do is come up with a way to actually convert the shared secret number both people come up with to an actual set of 3 numbers for the Enigma machine. There's a ton of ways we can do this. I'm just gonna kind of do it ad hoc here, and if you want to change your implementation, you can definitely do that. So since our biggest prime number is a 5-digit number, it's like 56,000 something, the biggest value of our shared secret key is also 5 digits. So let's first consider the case where we have a 5-digit number, because at the end of the day, we need 6 digits as well. So let's say we have a 5-digit number, so 5 digits. We have something like A, B, C, D, E. We could convert this into the 3 settings like AC, BD, EE, or something like that. And this is just, again, you know, we're taking these 5 numbers and then just like scrambling them up in some way to make the machine settings for the Enigma machine. Let's see if we have 4 digits. Maybe we have ABC, BB, AC, DD, 5A7. And where this is like a concatenation, so like if A is a 2, this setting would be 27, 25, 21, you know, something like that. So these will be the rules that we'll use once we get our shared secret key. We'll treat that as like a string and then parse it into these 3 pairs of numbers. So, and that's actually probably going to be something we need on the GUI as well, our spaces for this final parsing. So let's do that right now. Okay, and so once we get the shared secret key, this should just automatically be filled in as well. So we can just add the code for doing all of this in the generate shared secret key method. Generate a shared secret key. Okay, this time we had a 5-digit number. Let's check if that matches the 5-digit encoding. So it should be AC. So the first digit and third, yep, 22. That looks good. CB, so third and second, which is 21. That looks good. And then D, EE, which is the last one twice, which is 11. Okay, that looks good. Oh, one thing that's interesting here is I'm changing the private key. And when I'm regenerating the shared secret key, it's not actually updating. Because I think when we're clicking this, we're not rereading from this text box. That's something we should probably change too. Whenever we generate the shared secret key, we should also probably reassign the private key as well by rereading it from the text box. Let's try this again. Generate the modulus base pair, private key 3333. Say the public key similar, but one less. Okay, and then if I make this a 4, I should get a new secret key when I click this, and I do. Cool. Okay, so it looks like we're getting a shared secret key. We're converting it into 3 settings that we can then pass over here. And actually, you know, what would be nice is if we just could. We shouldn't have the user type these in. We should just pass these settings all the way over to this tab here. So let's do that as well. Let's try it again. So we'll generate a modulus base pair, generate a private key, get a public key, copy it, maybe make this a 3. We got this shared setting 277099, 277099, and we have an encryption setting that should only work here. And if we change this even a little bit, it's garbage. And one other thing I forgot we need to do is that, again, when we run this app, only one person is going to be generating the modulus and base. So one person will generate it, and so they'll populate these fields by clicking this button, but the other person will actually receive these, and they'll be typing them in themselves. So anytime we're doing any sort of math with the modulus or base, we always want to be reading it from this text box and not just assuming that it's always been already been loaded into its variable in the program. So let's just add those here as well. Right, so our modulus and our base and yeah, that should be good. We just need to add those 2 things for the person on the receiving end of the modulus and base pair. All right, that's the end of the video. I think this turned out to be a lot longer than I expected, and I'm guessing after editing, the final video is going to be a bit of a mess. So I'm going to just apologize about that in advance, and thank you for those who watched this video all the way through. Thanks to those who watched the video just for the beginning, for the demo at the beginning, and to all the people that watched the entire series from start to end. I really appreciate it. And I hope if you get anything from this, you either get some entertaining app you can use to send secret messages back and forth with your friends, or you just learn something cool in general about cryptography or programming or anything like that. So again, thank you all for watching. I'll link the source code in the description of the video below, and I'll see you guys next time. Bye.